Welcome to our deep dive into the world of mathematical proof. We're going on a journey through history to uncover some groundbreaking theorems, but with a twist.
Oh,
We won't just focus on the formulas, but on the stories and the strategies behind these mathematical breakthroughs.
okay. Sounds good.
You shared some excerpts from a book called Journey Through Genius. That's
Yeah.
The Great Theorems of Mathematics by William Dunham.
Right.
We'll use that as our guide as
Oh,
we
sure.
explore the brilliant minds, behind the math.
Yeah. This is what's so cool. We think of math as like rigid and dry, but it's a human story,
Right.
full of creativity, facing challenges, and those aha moments when you discover something new.
Exactly. Those aha moments. Right.
Yeah.
That's what we want to dive into. So let's start way back with the ancients.
Okay.
The Egyptians and Babylonians,
Way back.
they were masters of practical math. Think like measuring land or building pyramids, right?
Their approach was mostly like following a recipe, though. Their texts are like full of instructions, but rarely explore the why behind the how. You know what I mean?
Oh, interesting.
Right.
Okay.
Yeah.
So then the ancient Greeks came along, right? Like around the 6th century BC.
Yeah.
And they weren't content just knowing the steps. They wanted proof. They wanted to know why their solutions worked.
Exactly.
Enter Thales,
Yeah.
often called the father of demonstrative mathematics.
Yeah, he was basically the first to say, hey, show your work.
Right.
Don't just give you the answer. Explain how you got there.
Okay, but how do you really show your work when you're trying to measure like a pyramid?
Right.
I mean, that's a pretty big show your work problem.
That's right.
There's a famous story, right, about Thales being challenged to measure the height of the Great Pyramid.
Right.
And he did it using just his knowledge of geometry and some clever observation.
Oh, yeah. We've all heard that one.
Mm-hmm.
Instead of like climbing the pyramid with a tape measure,
Right.
he used its shadow.
Exactly. Thales realized that when the pyramid's shadow was the same length as his own shadow,
Uh-huh.
he could use like that relationship to calculate the pyramid's height.
Right.
That's thinking outside the box, right?
Absolutely. It's like he turned the pyramid into a giant sundial.
And that leads us to the Pythagoreans,
Yeah, the Pythagorean.
a group absolutely obsessed with the beauty and order of whole numbers.
Oh, they loved whole numbers.
Right. They believed that whole numbers, 1, 2, 3, were the basis of the entire universe.
They were convinced that all lengths could be expressed as ratios of whole numbers.
Uh-huh.
You know, any two lengths could be divided into smaller, equal units. This is called commensurability. Seemed pretty obvious to them.
But as they delved deeper into geometry,
Yeah,
they made a discovery that totally shook their worldview.
it did.
Imagine their surprise when they found lengths that could not be expressed as ratios of whole numbers.
Right. It was a huge blow to their understanding of the universe.
Yeah.
Imagine you find out that the building blocks you thought made up everything don't actually work in all cases.
So these incommensurable lengths,
Yeah.
which we now call irrational numbers, right, threw a real wrench into their nice, neat, and tidy world.
Yeah, it did.
And this brings us to another famous Greek mathematician,
Okay.
Hippocrates of Chios.
Not the Dr. Hippocrates.
Doctor.
A different one.
This guy was a brilliant geometer.
Yeah, he was obsessed with this idea of squaring shapes,
Okay.
which means using only a compass and a straight edge to construct a square with the same area as the given shape.
Yeah, I can see how that would be a real brain teaser.
It would be.
And Hippocrates, he managed to square this bizarre shape called a lune.
Orlun.
It's like a crescent moon, right?
Yeah, basically, if you take a bite out of a round cookie, that shape you're left with,
And what's remarkable is that he did this using only basic geometric principles.
will be impressive, right?
Yeah. This was a big deal because it was the first time anyone had squared a shape with curved sides,
Uh-huh.
and it made mathematicians think, hey, maybe we can square anything, even a circle,
Right. And that kicked off this, like, centuries-long quest to square the circle.
which turned out to be impossible.
Impossible.
But it led to some amazing discoveries along the way, right?
Oh, yeah. Like, the distinction between algebraic numbers,
Mm-hmm.
like whole numbers, fractions, roots, and transcendental numbers, like pi.
So squaring the circle became like the mathematical white whale.
Exactly. But proving its impossibility was no easy feat.
Uh-huh.
That's where Ferdinand Lindemann comes in.
Okay.
In 1882, he showed that pi is transcendental.
Okay.
which basically means it can't be constructed with a compass and straight edge.
So you couldn't use those tools to create a square with the exact same area as a circle.
Right.
So a dead end for squaring the circle,
Yeah.
but a huge leap forward in understanding numbers.
It was.
Okay. Speaking of giant leaps, let's talk about Euclid.
Okay.
His book, The Elements, was like the math Bible for over 2,000 years.
It was.
It wasn't just his discoveries, it was a collection of Greek mathematical knowledge, all organized into this logical system.
Right. He took all the best ideas and put them into this beautiful interconnected structure, and it was all based on rigorous proof.
And probably the most famous part is his proof of the Pythagorean theorem.
Oh, yeah. The Pythagorean theorem, everybody knows that one. A squared plus b squared equals c squared.
Right. But maybe not proven so elegantly before Euclid.
That's right. His proof is brilliant. It uses only the simplest concepts he built up earlier in the book.
It's like constructing a complex building from just a few basic materials.
It is. You can't help but admire the ingenuity.
Yeah. And he didn't just prove the Pythagorean theorem, he also proved the converse.
The converse.
Which means if a triangle has sides that fit the theorem,
Okay.
it must be a right triangle. So it works both ways.
Quiz.
Euclid's dedication to logic and completeness, right,
And seen in his work.
really shines through.
Definitely.
And let's not forget his work on prime numbers. He proved that they are infinite,
Infinite.
meaning there's no biggest prime number.
They just keep going.
They just keep going, going, and going. Okay, so we've got Thales with his shadows,
Right.
the Pythagoreans, and their obsession with whole numbers.
They loved those whole numbers.
Hippocrates squaring the loon,
That crazy loon.
Euclid organizing
The
everything.
great organizer.
And now we're ready for the rock star of ancient mathematics,
Oh, yeah?
Archimedes.
Archimedes.
He wasn't just a brilliant mathematician. He was an inventor, engineer, and physicist, a true Renaissance man.
I mean, he gave us the Archimedes screw, still used today to lift water.
Oh, wow.
And who could forget that famous eureka moment in the bathtub?
Yeah. The story goes, right, that he figured out how to determine the purity of King Hiram's crown
That's right.
while he was in the tub.
Got so excited he ran naked through the streets shouting, Eureka!
Talk about dedication to science. But beyond the inventions, right, he made huge contributions to geometry.
Huge contributions, like figuring out the area of a circle and getting a really accurate approximation of pi.
Oh, wow.
He was able to connect the problem of the circle's circumference to its area, which even Euclid seems to have missed.
How did he do that?
He used something called the method of exhaustion.
Okay.
Imagine squeezing a circle between polygons with more and more sides.
Okay.
He kept increasing the number of sides, getting closer and closer to that circle.
Oh, so it's like fitting a round cookie cutter
Huh?
into a square, then an octagon, then a shape with 96 sides.
And he did all this without calculators or computers.
Wow.
Just pure brain power.
Yeah. So by doing that,
Yeah.
he got an incredibly accurate approximation of pi.
He did.
It's a real testament to his dedication to mathematical precision.
It is. And it paved the way for future mathematicians to explore pi even further.
And that's just the beginning of his story. Next time, we'll dive into some of Archimedes' other mind-blowing work, like his discoveries about the surface area and volume of a sphere. Welcome back to our deep dive into mathematical proof. Last time we were talking about Archimedes,
Archimedes.
the rock star of ancient math, right? He was known for his inventions like that, Archimedes screw,
Yeah.
but he also made some major discoveries in geometry.
He did. We were just talking about how he connected a circle's circumference to its area.
Right, something that even Euclid seemed to miss.
Right. And he used that method of exhaustion to get a really good approximation of pi.
Squeezing that circle between polygons with more and more sides.
More and more sides.
But his genius doesn't stop there. He also tackled the surface area and volume of a sphere.
Oh, yeah, the sphere.
Talk about complex shapes.
He was a master of visualization.
Yeah.
Think of a tennis ball fitting perfectly inside a cylindrical can.
Okay.
Archimedes showed that the sphere's surface area is exactly 4 times the area of the circle, like slicing through its equator.
So if you took 4 of those equatorial circles and stuck them together, you'd get the same area as the entire surface of the sphere.
Exactly. And he didn't stop there.
Wow.
He also proved that the sphere's volume is 2/3 the volume of that cylinder it fits in.
It's amazing how he could see these connections between shapes, right?
It is.
Okay, so we've got Thales with his shadows.
Yeah, Thales and his shadows.
The Pythagoreans with their obsession with whole numbers.
Those whole numbers.
Hippocrates squaring the lune.
Uh-huh.
Euclid organizing everything.
Keeping it all neat and tidy.
And Archimedes pushing the boundaries of geometry.
A real mathematical powerhouse.
What a lineup. But there's one more ancient mathematician we got to talk about.
Okay, who's that?
Heron. Have you heard of Heron's formula?
Ah, Heron's formula. Yeah, it's kind of a hidden gem in the world of geometry. It lets you calculate the area of any triangle.
Okay.
If you know the lengths of its sides.
So no need to measure angles or draw altitudes?
Nope, no need for that. Just the sides.
That sounds pretty handy.
It is. But the formula itself is kind of strange. It involves something called the semi-perimeter.
The semi-perimeter.
Which is half the sum of the sides. And then there's a square root in there.
Okay.
It's not immediately obvious why that would give you the area.
So where's the hidden gem part?
The real beauty is in the proof, Heron's proof. It's this long, winding path through all these different geometric propositions.
It's like a mathematical mystery novel.
It is. You're reading along and you're like, where is he going with this?
And then, bam, he shows how it all comes together to give you the area of the triangle.
Exactly. It's a testament to his deep understanding of geometry and his ability to see connections that others might miss.
He deserves more recognition, right? Heron, that guy was sharp.
He was. Okay, so we spent a lot of time in ancient math.
Yeah, we have.
Let's fast forward a bit, see how math evolved over the centuries.
Okay, so what happened after the ancient Greeks?
Well, things got really exciting. We see the rise of algebra with its powerful symbols and its ability to solve more and more complex equations. And then there's calculus.
Oh, calculus.
This revolutionary tool for understanding things like motion, change, continuous quantities.
Calculus changed everything. It led to so many advances like in physics and engineering.
Absolutely.
But this period wasn't without its share of drama.
Oh, yeah, that's right.
Remember the Newton-Leibniz controversy?
Oh, the great calculus feud.
Right.
Newton and Leibniz both developed calculus independently. But then there was this huge fight over who deserved the credit.
It's a good reminder, right, that even in the world of logic and reason, there's still plenty of human passion and competition.
There is.
Especially when it comes to, who gets the glory.
Who gets the glory, that's right.
Speaking of colorful characters, we can't forget Cardano.
Cardano. Oh, yeah.
Yeah.
He was a doctor, a gambler, an astrologer.
He was a brilliant mathematician.
He was.
This guy cracked the code of cubic equations.
He did. Figured out a general formula for solving them. A problem that had stumped mathematicians for ages.
That's huge.
It is.
And didn't he have to, embrace imaginary numbers to do that?
He did. Which were pretty mind-blowing at the time.
Yeah. Cardano's work really shows that sometimes you got to challenge the rules.
You do.
Accept new ideas, even if they seem strange.
To make real progress in math.
Yeah.
Okay. Well.
So we've got algebra, calculus, shaking things up.
Yeah, shaking things up.
But then the 19th century comes along, and there's another major change.
What's that?
The emergence of non-Euclidean geometry.
Oh, yeah, non-Euclidean geometry. This is a paradigm shift.
Right. For 2,000 years, Euclid's Elements was seen as,
the truth.
The absolute truth about geometry.
And then mathematicians started exploring alternative geometries.
Where Euclid's postulates, his basic assumptions, didn't hold true anymore.
It's like trying to imagine a world where parallel lines could actually meet.
Ooh.
Seems counterintuitive.
Yeah.
But these non-Euclidean geometries turned out to be completely logically sound.
And they actually have applications in, physics and cosmology.
They do.
So Euclid's truth wasn't the only truth, after all.
It's a good reminder that there are multiple ways of looking at things. And then we have Georg Cantor, who took on this mind-boggling concept of infinity.
Oh, infinity. Yeah, that's a big one.
His work on set theory and transfinite numbers is really incredible.
So he developed a way to compare the sizes of infinite sets.
He did?
And found that some infinities are actually bigger than others.
That's right.
Wait, hold on. How can one infinity be bigger than another?
I know, it's a tough one to wrap your head around.
It is.
He used this technique called the diagonalization proof.
To show that the set of real numbers...
Yeah, all the numbers on the number line.
...is more numerous than the set of natural numbers.
That's right. 1, 2, 3, and so on.
Wow. So there are, different levels of infinity.
Different levels.
That's wild.
It's a concept that takes some time to digest.
Yeah.
Cantor's ideas were pretty controversial at first,
Huh?
but they ended up revolutionizing our understanding of infinity.
And laying the groundwork for uh, modern set theory.
They did.
It's a reminder that sometimes the most groundbreaking ideas are the ones that challenge our basic assumptions about the world, right?
Absolutely. You got to be
Yeah.
willing to question what you think you know.
From ancient Greece to the 19th century, right?
Yeah.
We've seen these mathematicians pushing the boundaries of what we know about numbers and shapes, and even infinity.
Yeah. It's incredible how math has evolved over time.
And it's not just the formulas and theorems, right?
No, no.
It's about the human stories, the creativity, the challenges, the aha moments.
The aha moments, that's what it's all about.
That's what makes this so fascinating. We
Yeah.
get to see the human side of math, right?
Exactly.
So let's bring it back to our listener.
Okay.
Why should they care about all of this?
Well, it shows us the power of human reasoning, right?
Mm,
These mathematicians were grappling with some really fundamental questions
yeah. Questions about the nature of the universe.
about numbers, space, even infinity.
Right. It's about more than just, memorizing formulas.
So much more.
It's about using logic and critical thinking to understand the world around us.
That's it. And that kind of thinking, it's not just useful in math class.
It's valuable in any field.
Yeah. Whether you're solving problems at work or making decisions in your personal life, that ability to think critically is crucial.
It's like what we saw with
Yeah.
Cardano embracing imaginary numbers.
Or those mathematicians questioning Euclid's postulates and coming up with non-Euclidean geometries.
Right. It's about challenging assumptions and not being afraid to explore new ideas.
Even if they seem strange at first.
Okay, we've covered a lot of ground in this deep dive.
We have.
Pair
From ancient Egypt.
the mind-bending ideas of Cantor.
But we want to leave you with one final thought.
Okay.
Something to ponder as you continue exploring the world.
Okay.
Think about those different sizes of infinity.
Yeah.
What does that tell us about the nature of mathematics?
What are the limits of what we can know?
It's a mind-blowing concept.
Yeah.
Maybe it's a reminder that there's always more to learn, more to discover. The journey never really ends.
Keep exploring. Keep asking those questions.
Yeah.
And never lose that sense of wonder.
That's the key.
The world is full of incredible secrets.
Waiting to be uncovered.
Until next time.
Happy deep diving.